promised you I was going to skip air traffic control details, so here we go, skipping about a little. This is, again, history. This was the first big success story for us from 2000, but that's a system that we are now in the process of replacing. It was Ada. We reused a lot of that Ada code. That system was Ada 83, and we're replacing it with a system that is in Ada 95. We looked at stepping up to Ada 2005, but we didn't feel that the features that were added for 2005 were needed enough in the current system to justify. As those of you who build humongous systems know, there's a lot of inertia of this big systems vendors or customers who are reluctant to change. So at the beginning of a program that lasts years, you select a compiler, tools for doing architecture, design, and so on. And then there is very much resistant to change in the middle unless there is a very good reason. So you might be able to upgrade versions of a compiler because the previous one is end of life or something, end of support, or you might be able to upgrade hardware for the same reasons. But switching tools, design tools, or language, or too drastic of a change is not usually looked upon favorably. All right, URET is kind of sort of has a lot in common with, you've heard today several mentions of IFACs for the UK, but it's a medium-term conflict detection tool that it's, the architecture is different, certainly, and this is Ada 95, not Spark, but it is Ada. This is just one of the displays showing a red conflict that's violating separation minima, and a yellow conflict, which the threat of violation is somewhat less. Okay, so now I have a few pages on the system that I'm currently building, but really it achieved government acceptance at many of those 20 sites, and sometime this year we will achieve what's called initial operational capability, which basically, and in-service decision even this year, which basically is a point where FAA decides, all right, this is it, system is going live, and once that decision is made, basically in rapid succession, all the sites go live with this new system. So things are going well. If you heard some of this pitch before, if you read the literature or the web from the Federal Aviation Administration, we are on budget and ahead of schedule. It doesn't feel like that when you're in the lab, but apparently we are ahead of schedule and on the budget. All right, so these are just why are we doing it? Well, it's the usual. You always replace a system because the prior system, the hardware is obsolete. You've tried to extend the life by doing a little upgrade, but then you also need additional new features, and over a period of years, you build up enough consensus to replace the existing system with a new one that you finally get to it. This is a caricature that shows that those 20 systems I told you about are the same. Each one basically has that one control center. It's redundant. So the fact that there are 20 is only because because the United States is large. But in any one place, we have the two channels are for purposes of fault tolerance redundancy, but mostly for 24/7 operation. In other words, we can use a single channel. A single channel in and of itself meets all the availability requirements. It is fully redundant. The other channel is available for doing testing of new releases, for taking offline, for replacing hardware and such planned activities. But if there are no such planned activities, then even that channel, the alternate channel, is acting as a backup, getting the data synchronization from the currently active channel, and can be quickly switched in case of need, okay? And so in addition to the operational system, that's majority of which is in Ada, then there is a test and training microcosm, which if you go to one of these centers, there's a whole separate room with the same hardware and so on, where you test. All the air traffic controllers need frequent refreshing tests to bring them up, refresher classes on changes in the added features or changes in the system. So there's a whole test and training microcosm, not to mention for actual initial testing of new releases. And the support, so that's mostly in Ada. And the support environment is the environment that initially we use in the factory to build the system. All the tools to do compilation and standards checkers and doing the excuse me, unit testing and code coverage, all of those, that's all the support environment, as well as building releases for sending them out to the 20 centers. And all of that is in Ada. Not exclusively in Ada, we have some scripts sprinkled in here and there, and there is some C, C++. And now we are in what we call Release 2. So Release 1 is not live yet, but we are already developing Release 2, which will be operational sometime in 2010. And in there now we're adding some service-oriented architecture components that brings in somewhat more Java than we, here we have hardly any, practically no Java. Okay, well, we basically covered this. I think I'm gonna just move on, but all the architecture and design, as per usual for system architecting, you need to know what are your key driving requirements, why are you looking to have so much redundancy, and it's the usual fault tolerance and continuous operation and performance and system analysis, because you can't stop the system to figure out what's wrong with it. You have to do it offline with data recorded all the time. All right, I'm going to skip this. This is certainly too much detail for you for the hardware architecture, but it just depicts the fact that they are fully redundant. On a single channel, there is redundancy of servers, and then there are two whole channels that are connected. They meet at the display. So for air traffic controller, for one view, there are two computers servicing that view. One computer is on one channel, the other computer on the other channel, and the controller can, with a key sequence, look on this channel or the other. In case one of the computers itself fails, then it can quickly switch over to the other.